Good morning and a very pleasant day to our lecturer and fellow classmates. Today, my group and I will be presenting our topic, which is classification of polymer. Before we begin, polymers are very important materials that play a major role in our daily life. Whether we realize it or not, many products around us are made from polymers. For example, polymers can be found in packaging materials, plastic products, clothing fibers, medical equipment, automotive components, and many other industrial applications. Because polymers are used in many different areas, understanding their characteristic and classification is very important. Therefore, throughout this presentation, we will discuss the basic concept of polymers, different polymer classification, molecular structures, polymerization process, and copolymer concepts. We will also understand how polymer structures influence their properties and behavior. So now, without further delay, let us begin with the first topic.
This slide will be presented by myself, Awang Iman Irfan bin Awang Hasbibullah, and my metric number is 2025470268. And next group member is Abang Asfa Farish bin Abang Yusdi, and his metric number is 2025283956. Our last group member is Muhammad Syafiq bin Muhammad Suib, and his number metric will be 2025462158.
Section 01, Basics and Origin Classification. Understanding the fundamental units and how polymers are categorized by their raw source and environmental footprint. First of all, let us understand what a polymer actually is. A polymer is a high molecular weight macromolecule formed by linking thousands of tiny repeating structural units called monomers. These monomers are connected together through strong and permanent covalent bonds formed during polymerization reaction. To make it easier to understand, we can think of a polymer as a very long chain where each monomer acts as a small building block. When many repeating units join together continuously, they form a large structure called polymer. Besides that, unlike simple small compounds, synthetic polymers display a wider range of molecular chain length, which can be analyzed using the polydispersity index, or PDI. Furthermore, polymer architecture governs several macroscopic behaviors such as a high tensile strength, elasticity, thermal stability, and variable crystallinity. This means the structures and arrangement of polymer chain affect how the material behaves physically. Therefore, understanding polymer structure is important because it explains why polymers can have different properties and applications. Now that we understand what a polymer is, let us move on to the next topic. Next, we will discuss classification frameworks. Classification is important because polymers exist in many forms and have different structures, characteristics, and properties. Since polymers are broad materials with various behaviors, scientists and engineers classify them into several categories so they can be studied and understood more effectively. Firstly, polymers can be classified by origin. This classification divides substances according to natural availability, synthetic production, or artificial modification of existing natural structures. This means polymers can be grouped according to where they come from and how they are produced. Secondly, polymers can also be classified by structures. In this classification, molecules are categorized according to their three-dimensional geometry, such as linear straight chain, branch configuration, and interconnected cross-link networks. Since molecular structures affect the arrangement of polymer chain, it also influences their physical and chemical properties. Lastly, polymers can be classified by forces. This classification evaluates polymers according to mechanical and thermal actions as well as intermolecular forces. Examples include elastomers, fibers, thermoplastics, and thermosets. Therefore, this classification framework helps scientists understand polymer characteristics and determine suitable application.
Next, let us discuss polymer classification by source. This classification focuses on where polymer originate and how they are produced. Understanding the source of polymer is important because it helps us identify the origin and understand how different materials are developed for specific use. Firstly, natural polymer are polymers that occur naturally in biological systems without human modification. These materials are produced naturally by living organisms and are widely available in nature. Examples include cellulose, starch, protein, and natural rubber. Cellulose is commonly found in plant cell walls and is used in paper products, while protein are essential biological polymer found in living organisms. Natural rubber is widely used in a product such as tires and doors because of its flexibility. Secondly, semi-synthetic polymers are derived from naturally occurring compounds that undergo specific chemical alteration. In this process, natural materials are modified to improve certain properties and characteristics while still maintaining their original source. Examples include rayon, which is cellulose acetate, and cellulose nitrate. Rayon is widely used in textile industry because it can be made into soft and comfortable fabric. Therefore, semi-synthetic polymer combine natural source with human modification to produce improved material. Lastly, synthetic polymer are man-made macromolecules entirely synthesized under laboratory conditions from petroleum products. Examples include polyethylene, nylon 6, and PVC. These materials are commonly used because they can be produced on a large scale and tailored according to industrial needs. For example, polyethylene is widely used in plastic bags and bottles. Nylon 6 is used in rope and engineering products, while PVC is commonly used in pipes and construction material. Therefore, classification by source help us understand where polymers come from and how they are produced. Now, let us discuss impact of molecular geometry. The structural arrangement of monomers strongly affect density, packing efficiency, melting point, and tensile properties. In simpler words, the arrangement of polymer change influence how molecules interact with one another and determine the overall behavior of the material. For example, linear configuration pack tightly together and display high crystalline properties. Since these chains are closely arranged, stronger interaction occur between molecules, making the material stronger and denser. On the other hand, branch change decrease packing efficiency and lower structural density because the side branch creates space between polymer chains. As a result, molecules cannot pack tightly together and the material becomes lighter and more flexible. Meanwhile, cross-link architecture completely alters physical form by turning thermoplastic chains into solid and insoluble three-dimensional network. Due to this structure, polymer chains become strongly interconnected and cannot move freely. For example, cross-linked polymers are commonly found in materials requiring heat resistance and structural stability. Therefore, this shows that even small differences in molecular geometry can significantly influence the physical properties and application of polymer. Next, this slide shows the relation between polymer structure and physical properties. Different polymer structures produce different characteristics because the arrangement of polymer chains affect how closely the molecules can pack together. Firstly, linear chains have very high packing density, high melting point, and excellent tensile strength. This is because the chains are arranged closely together, creating strong intermolecular forces. Examples are HDPE, nylon 6, and PVC, which are commonly used in pipes, bottles, ropes, and construction material due to their strength and durability. Secondly, branch chains have low or loose packing density, lower melting point, and moderate tensile strength. The side branch prevent tight packing, making the material softer and more flexible. Examples include LDPE and deep tail. LDPE is widely used in plastic bags and flexible packaging material. Lastly, cross-linked polymer have rigid and fixed structure. They do not melt easily and are strong, but brittle because the polymer chains are connected in three-dimensional network. Examples are bakelite and melamine, which are used in electrical switches, cookware handle, and kitchenware because of their heat resistance. Therefore, different polymer structure directly affect their physical properties and determine their suitability for different applications.
Now, let us move on to polymerization and copolymers. Polymerization refers to the process in which monomers combine to form polymer chains. This process is important because it converts small molecules into larger structures that possess useful properties for various applications. Firstly, addition polymerization, also known as chain growth polymerization, occurs without the loss of molecules during the reaction process. One example is polyethylene. In this process, monomers continuously join together one after another to form long polymer chains. In addition, the process dominates bulk commodity production with a share of approximately 72%. Polyethylene produced through addition polymerization is commonly used in plastic containers, plastic bags, and packaging materials. On the other hand, condensation polymerization, also known as step growth polymerization, involves stepwise bonding and release simple molecules such as H2O or HCl during the reaction process. Examples include polyester and nylon. This process contributes around to 22% of production share. For example, polyester is commonly used in clothing fibers and textile products, while nylon is used in ropes, fishing lines, and engineering applications. Therefore, although both methods produce polymers, they involve different reaction mechanisms and byproducts, resulting in different materials properties and uses. Finally, let us discuss composition and copolymer layouts. This classification focuses on the arrangement and types of monomers present within polymer chains because different monomer composition can affect polymer characteristic and performance. Homopolymers are composed of only a single repeating monomeric species throughout the backbone. One example is pure polypropylene. This means the entire polymer chain contains only one repeating type of monomer. Due to the uniform repeating structure, homopolymers generally display more consistent properties throughout the material. Meanwhile, copolymers are synthesized from two or more distinct monomers and can exist in alternating, random, block or graph configurations. Examples include ABS and Buna-S. ABS is commonly used in helmets, automotive parts, and electronic casings because it combines strength and toughness. Buna-S is widely used in tires due to the durability and wear resistance. Therefore, different monomer arrangement and combination can influence the overall properties, performance, and application of polymer materials.
With that, we hope this presentation has improved your understanding of polymers. Thank you for your attention and we appreciate your time.